So I'm gonna talk now. We have finished section 1, 2, and 3 now. So I'm going to talk a little bit about associated shaft components. So when you have the shaft, you have the gears, you have the bearings, you have different components. You need to kind of attach them together. You need to make sure that the power is transmitted from the gear to the shaft, and then the forces flow to the bearings. Okay, so we need to have a means of transmitting the power or the torque from the gears to the shaft, or from the shaft to the gears, right? So one way of doing that is to use shaft keys. Okay, so what you see here, you see this is the shaft. Okay, so this is the shaft, and this is the hub. What's the hub? The hub is part of the gear. So the gear, when you have the gear, it is something like this. It has a hub here. So let me just draw it nicer. So let me just draw here. So for example, if this is your gear, and then you have here in the middle, like it is hollow, so that the shaft can go in here. And then this portion here, this portion here is called the hub. Okay, this part is called the hub. And then here you just have the gear. Okay, the rest of the gear. So we want here to, we want the shaft to go inside here. Okay, but if the shaft and the gear are not attached together somehow, so the shaft is going to rotate, but the gear is not going to rotate. So in order to make sure that we transmit the power from here to here, so these two have to be attached. And this attachment is this using some keys here. So the first one on the left is called the square key, where the width and the height are equal. The width and the height here of this the key are equal. So the key is just a cuboid shape, something like this. This is kind of a square key. Okay, and this there is a kind of the keyway. If you remember, the keyway is just a slot on the shaft. So if, for example, if this is the shaft, then there should be some slot, guys, here inside. Okay, so if this is the shaft, so, and this here, this key goes here into this slot. Okay, so the second part here, okay, the second type, sorry, is the flat key. The flat key is like W and H are not equal, so the height and the width are not equal. But there are some recommendations here. For example, the width of the key here is equal to 1/4, approximately 1/4 of the diameter of the shaft, because this comes later. I mean, the key comes later. After you design the shaft, you have the diameter and everything. In the flat case, you have here the width is 1/4 of the diameter of the shaft, and the height, which is H here, is equal to 3/4 of W. So H here is 3/4 of W, which is the width of the key, right? We have round key as well. You can have it like this. It's just round. It's like a pen that goes between them. We have another type called Kennedy, or Kennedy's key. The Kennedy key is like for heavy duty services. You have two square keys here on the sides of the shaft. We have another type called Woodruff key. It is like a semicircle. It is like something like, I'm not sure whether I'll be able to draw that or not, but let me just try. It is something like this, guys. It is like, and this key here goes in like a semicircle slot that is in the shaft. And then you see here, this is the hub of the gear, for example, or the pulley, and this is the shaft, okay? And then this is the key that is used to, sorry. So this is the key that is used to transmit the power between the shaft and the hub. Okay. Without this, you have two circles. You have the shaft here, and then you have the hub. If you don't have anything between them, so this will rotate in this direction, and this is not going to rotate because nothing is between these two transform or transmit the power from here to here. There is nothing. So we have to use these kind of components. There is one more shaft, there is one more key type. It's called the gip head key, the gip head key. This is, it has a specific head here, and it has a specific slope as well. So usually it is tapered, and when you just fix the or attach the gear here, so you just need to push either the gear in this side or to push the gip key in this side, so that you have here just they tie together. They get tied together. One more time is called feather key. The feather key here is like similar to the square key, but the thing is that they use screws to fix it with the shaft. And then in this case, the hub is free to move axially. So the hub itself can move in the axial direction. So, and also if you, it makes it easy even if you have two. So you have one feather key on the top and after 100 degree, or on the opposite side, you have another feather key. So this allows if you wanted the hub or the gear to move to the left and to the right, as in when you shift gears for the car, for example. Then we have also other types. We have bends. So this pen, for example, we have a straight round pen that goes, you see again, this is the shaft, and this is the hub of either the gear or the pulley, and then you have a slot between them, and then you drop the pen here, or the round pen. This pen can be tapered as well. So you have a tapered slot, and then this is the hub, this is the shaft, and then so this is the hub, and then you have this tapered pen that goes between them. This pen can be split tuber as well. So this is like a spring, you know. So because you have a slit here, or you have a gap here between these two sides, then when you insert this into here, into this circular gap, if you want, so this becomes like, it is compressed, and it becomes like a spring, a compressed spring. So it is fixed properly between these two parts. Also, there is one more shape here that is called grooved pen. So the grooved pen here has, you see, it has some grooves here. And then again, it is like when you insert this into the circular gap here, and then you keep pushing this from the top. So these two edges, they just come closer, and these two edges come closer, and it becomes like a spring again that just kind of, it becomes like a spring motion, okay, a spring action motion. Other types for actually locating the gear, for example, or the bearing, is called retaining or snap rings. So the snap ring actually is used to make sure that for example, the bearing doesn't move out of the way. So, for example, if this is the shaft, let me just draw one thing here. Okay. Just one moment, let me draw this. So if this is one side of the shaft, and you have a bearing here, let's say we have a deep groove ball bearing here, where it is drawn something like this. We'll talk about this later, but now we have, let's say we have a bearing here. Then the rest of the shaft is here. So this retaining or snap ring goes here, goes in this groove. Okay, so something similar to this. So, and this, when you install this snap ring here, so this bearing cannot move out of the way, because the ring is going to be here, and so the bearing cannot go out of the way. Okay, let me just get rid of this for a moment. So what we have here, guys, we have different types of snap rings or retaining rings. We have a basic type. So you see there is a caliper that just opens these two so that you can fix it, or you can put it in the groove next to the bearing. Again, here as well, you use a specific caliper to open this until you install it, something similar to this. For example, you install it on the shaft. So this is the shaft in this case. And then there is a groove here that I've shown you earlier. Okay, so there are various types. So this is called inverted, this is basic, and this is basic and inverted, but this is for internal. So this fits in the housing. So you have sometimes sometimes snap rings that is used externally on the shaft, something like this type, or internally. So it can go through an internal groove in the casing, for example. And this is how it is shown here. And because you have, for each case, you have basic type and inverted type. So this graph here, this graph show you the standard and the inverted external snap rings, and this graph shows you the standard and the inverted internal snap ring. Also, there is one more ring called E-ring, so it's similar to this one. That is externally, if this is the shaft, for example. So again, it just snaps over the shaft to locate gear or locate a bearing and so on. So we have two more types of retaining or snap rings. This one, it is called, it is labeled as push-on type. This is push-on type. And then again, we have external one that goes on the shaft, on the external diameter of the shaft, or internal one that goes into the casing, for example, or the housing, right? So again, it is used to locate or prevent the bearing to move axially, or the gear to move axially, and so on. So these are the two types of push-on ring or snap ring, external one and internal one. Also, when you transmit the power from one component to another, you might use what's called splines. We are definitely going to use this in our project. So for example, if you consider the engine is here, and then this is your shaft, okay? And then this shaft is going to carry the gears and so on. So you need to transmit the power from the engine to the shaft. So you can design here what's called the spline, as you see it. And this is the real picture here, where you can see internal spline here on this hub of the gear. So this spline can be used, you have a male and female ones, and then they can be used to transmit the power from here to here. Okay, so we have different types of splines. We have 4 spline. So the names explains everything. So 4 spline means we have 4 splines, 6 splines, 10, 16, or involute. So this is similar to internal gear if you want. Okay. The last thing that I'm going to talk about today is the how you calculate or design a key. So you have a key and you have some forces, and then so how you design a key or find the dimensions of a key. So just imagine the key is something like this. So we have here we have a specific length of the key, we have a width, W, and then we have a height, H, small or capital, right? So just consider to find W, L, and H. So what we need to find these three values, right? So as I said earlier, if you remember, they consider W, which is the width, as approximately 1/4 of the diameter of the shaft, okay? Either capital or small, doesn't matter, okay? And then there is also a relation between H and W. This could be given if you have a square key, so W and H are equal for square key, okay? So if you have a flat key, so go back, it's a 3/3, so H is 3/4, sorry, of W, so for flat, okay? So I'm just gonna get rid of all this now in order to focus on the graph that we have. Then we have here, what we have? We have the hub, okay? So this is the hub. We have the shaft, all right? And then we have the key between them. This is the key, all right? So when the shaft rotates, so there is a torque that has to be transmitted to the hub. So when the shaft rotates, so there is a specific torque that has to be transmitted, and this torque is transmitted through this force here. So the shaft pushes this part of the key with a force F, and then there is a reaction force between the hub and the key with this force F, right? So the force F can be calculated based on the torque. You remember, it's torque divided by d/2, which is the radius. So if you have the torque, you have the diameter of the shaft, so you can calculate this force F. But now what we want to find is the dimensions. So we want to find the dimensions here, right? So we have two types of stresses. The first type of stresses here is the shear stress. So the force is trying to shear the key here, right? So this again, let me just draw this nice key, right? So if you consider here in the middle, you have an area that is going to be sheared. So this is the shear area. So the red here is the shear area. So this is, if you divide this key into two parts, so you have L and then you have W. So the area shear here is W times L. Okay, so this is the shear area. Also, we have between here, just go back. So between the hub and the gear here and this portion, or between the shaft and the key, so between the hub and the key, or the shaft and the key, there is like some sort of bearing stress. So it is shown here at the top half of this part. Okay, so two types of stresses now: shear stress, where the area shear is W times L, and we have bearing or compressive stress, where the area in this case is H/2 times L, which is this red shaded area here. It's 1/2 of the top part of this key, right? So the force can be calculated based on the diameter of the shaft and the torque. The torque, the area shear or the shear area is the width multiplied by L, and then the design shear stress, in this case, direct shear stress, is the force divided by the shear area, and the force is 2T/D, and the shear, the area of shear is W times L. So this is our first equation. In order to design the key, so this design stress has to be less than or equal S yield in shear over a factor of safety. Okay, so we can you can substitute this value here to the left-hand side of this equation. Based on the material of the key, we can find the yield strength in shear. For general applications, we can consider this as 2, and then we try to find here the dimensions. You see here the right-hand side of this equation is independent of H. We don't see H at all here into this equation. But again, as I said, simply you can consider L as your unknown, and then say W is equal to D over 4. So here in this equation, you know the W because you know D, and then L is your unknown. You'll find the critical length of the key. Then the failure due to compressive stress or bearing stress, the bearing area, as I said, or the compressive area is this shaded part of the key. It is 1/2 of the height multiplied by the length. And then again, the bearing stress is the force divided by the bearing area. The force is 2T divided by D. 2T divided by D is our force. And then divided by the area here that goes here. So eventually we have 4 times T over D HL. So torque, diameter of the shaft, height of the key, length of the key. Then this is our design equation where we see sigma design, which is the compressive or bearing stress, calculated compressive or bearing stress is less than or equal to the yield, S yield, over the factor of safety. So factor of safety can be considered here, as I said, 1.25 to 4. And then for general applications, it's 2. It has been decided here to be 3 anyway. So even if you choose S2 is as good enough. So again, from here, you say there is, if we have a square, 5 square key, so W is equal to H, is equal to the diameter divided by 4. So, and then from this equation here, you can find L critical. And then you compare this L value with the previous L value and choose the larger